Usually when we talk about a business problem, there's this expectation of precision, you know?
Right, like it should be binary.
Exactly. It's a lot like engineering. You have a broken piece of machinery, the mechanic points to the snapped belt, and they just say, well, there it is.
Broken or not broken, it's very comforting.
Yeah, a clean, visible diagnosis.
We inherently like things to be visible, right? To be categorized and to be solvable right in front of our eyes.
But then you step into the world of global supply chains, you know, the massive invisible webs that keep businesses running. And suddenly that clean diagnostic process is completely thrown out the window.
Oh, completely. It's a totally different game.
We're looking at a landscape of potential disasters that's frankly terrifyingly murky, mostly because the problems haven't even happened yet.
Right.
So how do you mathematically predict a disaster before it strikes? That is the mission for this deep dive.
I love that framing.
Thanks. We're taking the APCS CPIM Module 5 materials, specifically Section C, and breaking down the rigorous mathematical strategy that keeps supply chains breathing when the rest of the world goes sideways.
Which is arguably the most critical capability if you actually want a business to survive contact with the real world.
Yeah, no kidding. Okay, let's unpack this.
Okay.
Because today is all about risk management. And it's not just crossing your fingers, right?
Not at all. At its core, risk management in these complex supply chains isn't about, throwing unlimited money at every potential problem.
Right.
It's an economical balancing act. You're spending just enough resources to minimize, monitor, and control how likely a disaster is. And of course, how bad it will hurt if it actually happens.
That word economical is doing a lot of heavy lifting there. I mean, you can't just bubble wrap an entire global operation.
No, you'd go bankrupt.
Exactly. You have to be strategic. But before a business can calculate an economical response, it first needs to know exactly what the threat looks like, right? You can't manage a shadow.
You really can't. Which is why the risk management process isn't a simple checklist that you finish and file away.
Like a one-and-done thing.
Right. It's not that at all. It's a continuous loop of survival. It starts with a sweeping audit of your vulnerabilities. So identifying the risk.
Okay, step one, identify.
Yeah. You have to look at the external environment, your internal processes, the supply chain, the workforce, everything. Then you analyze those potential risks.
Looking at the impact and the probability of them actually happening.
Exactly. From there, you develop an appropriate response. Then you implement and monitor that plan using tests and audits. And finally, you assess the whole strategy to start the loop over again.
It never stops. So going back to the beginning of that loop, identifying the risks, rather than just listing out every possible catastrophe.
And there are a lot of them.
So many. The source materials break them down into categories, like external risks, which would be currency crashes or civil unrest.
Right, or theft.
Yeah. Then environmental risks, like natural disasters, floods, fires, environmental requirements.
Then there's technical risks, like equipment failures, power outages, IT systems going dark.
And organizational risks. Inadequate resources, poor supplier performance, plus legal and regulatory risks, like patent infringement or bribery.
It's a massive list.
Yeah.
But there are specific supply chain risks mentioned in the text, like loss of intellectual property or loss of reputation. And one more that's really critical.
I know exactly which one you're going to say, and it caught me completely off guard. Forecast inaccuracy.
That is a brilliant one to isolate.
I mean, I'm looking at this list of threats, right? I see natural disasters, theft, massive fires, and then forecast inaccuracy. A massive flood is a devastating act of nature. A bad forecast is just, well, it's bad math.
It sounds so mundane in comparison.
Right. Someone put the wrong number in a spreadsheet. How does a typo end up on the same threat level as a literal fire?
What's fascinating here is that in the context of a highly optimized global supply chain, bad math creates a shockwave. It destroys value just as thoroughly as a fire destroying a warehouse.
Wait, really? Just as thoroughly?
Oh yeah. Let's trace a mechanism. A massive forecast inaccuracy doesn't just mean you have, like, a few extra boxes in a stockroom.
Okay.
If you forecast demand too high, you suddenly tie up millions of dollars in capital.
Oh, wow.
That money is trapped in inventory that's just sitting there. You have to pay to store it, to insure it, and over time, that product degrades or becomes obsolete. You are bleeding real value every single day.
So the company essentially drowns in its own unsold product.
Exactly. And the opposite is just as deadly. If you forecast too low, you create severe bottlenecks. The raw materials aren't there when the factory needs them.
The factory stops.
The factory stops.
Okay.
You miss critical deliveries to your biggest clients. The cascading failure results in a massive loss of reputation. And in today's market, losing your reputation can bankrupt the company faster than rebuilding a burned-down facility.
Man, a bad spreadsheet really can burn the house down. That completely shifts how I view internal organizational risks.
It really highlights how fragile optimization can be.
So we have this massive, terrifying brainstorm of everything that could possibly go wrong, from civil unrest to someone carrying the one incorrectly on a demand forecast.
The panic is setting in.
The panic is definitely setting in. So how do we move from just guessing what to fix first to actually doing the math?
Well, we have to bridge the gap between subjective fear and objective data. Industry relies heavily on a specific tool for this, called the FMEA.
Which stands for Failure Mode and Effects Analysis, right?
Yes. The sources define it as a tool to evaluate a design process to identify and rank potential failures. Think of it as a mechanism to force that panic through a mathematical filter.
Okay, here's where it gets really interesting. That filter is a very specific formula that generates an RPN, or risk priority number.
Exactly.
This isn't just a manager guessing like, oh, how bad is this out of 10? The
No.
calculation from the text is a strict multiplication problem. It's the probability of occurrence multiplied by the severity of failure multiplied by the probability of escape from detection.
That multiplication aspect is the vital engine of the formula, because you're multiplying a high score in any one of those three categories drastically inflates the total RPN.
It instantly forces it to the top of your priority list.
Precisely.
Let's run the real-world numbers provided in the source data to see how this actually behaves.
There.
They give a scenario where goods are not secured. The team rates the probability of occurrence a 5 out of 10. The severity of the failure is a 6. But the probability of escape from detection is rated a 2.
So you multiply 5 times 6 times 2, and you get an RPN of 60.
Okay, so 60.
Keep that baseline in mind. An RPN of 60 for unsecured goods. Now looks a slightly different failure from the text. Goods incorrectly loaded.
Okay.
The occurrence goes up to a 7. The severity is actually lower than the first scenario, rated at a 4.
So it happens more often, but the immediate impact is slightly less severe.
Right. But the probability of escape from detection shoots all the way up to a 7. So 4 times 7 gives you an RPN of 196.
Wow. That is more than triple the risk score for something that has a lower severity rating.
It is.
The entire explosion in that number comes from that third variable, the probability of escape from detection. It's the most counterintuitive part of the entire framework.
Why do you see that?
Well, it's exactly like a leaky pipe. If you have a leaky pipe dripping directly onto your office desk, that is highly detectable, right?
Yeah, you see it right away.
You see the water immediately, you put a bucket under it, you call a plumber, the damage is, I don't know, $50. But if that exact same leaky pipe is hidden deep inside your drywall,
Oh, yeah. The hidden one is infinitely more dangerous.
it escapes detection. It drips for 6 months until the entire structural wall rots from the inside out and the ceiling just collapses on your head.
Yeah.
The silent nature of the failure is what makes it so deadly.
That is a perfect analogy, and that mechanism plays out identically in the supply chain. Those silent failures create significantly higher RPNs because the damage compounds over time entirely unnoticed.
Like the incorrectly loaded goods.
Exactly. Think about the two cargo scenarios. If goods are simply not secured at all, they might rattle around violently the second the forklift moves them.
Right, making a huge racket.
Someone on the dock hears it, stops the shipment, and secures the load. The failure was detected immediately.
The bucket goes under the pipe.
Exactly. But if they are incorrectly loaded, say heavy pallets stacked directly on top of fragile components, but shrink-wrapped tightly so it looks totally fine.
Oh, man.
The doors are shut, the seal's applied, and the truck drives for 3 days. By the time it arrives, the entire bottom half of the shipment has been slowly crushed into powder by its own weight.
That's brutal. The failure escaped detection until it was entirely too late to fix it.
Right, which is why the math prioritizes it.
So calculating this RPN gives a logistics team a prioritized list. We know the 196 demands more attention than the 60.
Yes, it gives you a ranking.
But, I mean, if I walk into a CEO's office and say, hey, we have an RPN of 196, they're going to ask what that means for the quarterly budget.
Of course they are.
A list of abstract numbers doesn't automatically translate into a strategy for hiring teams or deploying resources. We need to visualize the battlefield.
Which brings us to the next crucial tool in the sources, the risk matrix. The matrix takes those isolated RPNs and plots them on a graph.
Okay, paint a picture of this graph for us.
You have a horizontal axis representing the probability of occurrence running from low to high.
Okay.
And you have a vertical axis representing the magnitude of impact, also running from low to high. When you cross those, you create 4 distinct quadrants.
Let's populate this mental matrix using the examples from the material to see where things land. Top right quadrant, high impact, high probability.
Nightmares.
Yeah, the absolute nightmares. These are the threats that happen frequently and hurt badly. The text lists things like hazardous chemical spills, severe worker injuries, or chronic quality issues in base materials.
Then you move over to the top left quadrant. High impact, but low probability. These are the existential threats.
Like a meteor striking the factory.
Well, more like a total facility-wide disruption because a hurricane hit or the complete loss of all IT systems. It rarely happens, but if it does, the company might cease to exist.
Okay, so that's the top half. Then look down at the bottom left quadrant. Low impact, low probability.
The annoyances.
Right. The text highlights things like a minor regulatory fine or a secondary production line, let's call it line B, going down for an hour. It almost never happens, and when it does, it barely moves the needle on the company's daily output.
Placing the threats on the board is only half the job, though. The real strategic work, the part that answers the CEO's budget question, is choosing how to respond to each quadrant.
And the sources outline 4 strict criteria for this response, right?
Yes. First, the risk's magnitude. Where exactly does it sit on the matrix? Second, the probability of your proposed mitigation strategy actually succeeding, combined with the cost of implementing that strategy.
I want to stop right there on the cost element, because earlier in the process cycle, the materials outline 4 ways to respond to a risk: avoidance, transfer, mitigation, and acceptance.
All right, those are your 4 options.
I'm really struggling with that last one. Are you telling me a massive multi-billion-dollar corporation looks at a known threat on this matrix and intentionally chooses risk acceptance? Like they just shrug and leave the vulnerability completely open?
If we connect this to the bigger picture, they absolutely do. And it is a mathematical necessity.
Really?
Remember the core definition we started with. Risk management is the economical application of resources. You cannot mitigate everything.
Because you'd run out of money.
Exactly. Sometimes accepting a low-impact risk is the mathematically superior choice because the cost of mitigation would hurt the business's bottom line significantly more than the risk itself.
Okay, give me a concrete example of that trade-off.
Let's take that minor regulatory fine from the bottom left quadrant. Imagine the fine cost the company $5,000, and based on historical data, it happens roughly once every 10 years.
Okay, so $5,000 a decade. The total risk exposure is incredibly low.
Very low. But to guarantee that fine never happens again, the company would have to build an entirely new compliance tracking software system, hire a dedicated auditor, and slow down production for daily checks.
Oh, I see where this is going.
Let's say that mitigation strategy costs $50,000 a year.
You're spending $500,000 a decade to prevent a $5,000 fine.
Exactly. The cure is worse than the disease, so you intentionally accept the risk of the fine because spending money to prevent it is bad business.
You focus your massive mitigation budgets on the top right quadrant instead.
Right. The high probability, high impact threats where an RPN is screaming at 196.
That makes perfect logical sense. But it highlights a really uncomfortable reality about supply chains. Even with the sharpest RPN calculations, the most beautifully plotted matrices, and the smartest resource allocation, you are intentionally leaving gaps.
You have to.
Which means some risks are inevitably going to slip through. The hidden pipe is going to burst.
And when the disaster actually strikes, the theoretical phase completely ends. You are no longer managing a matrix. You are managing a crisis.
How an organization behaves in those first chaotic minutes dictates whether they survive. The text goes deep into recovery strategies, and it starts with the most critical phase, planning the first response.
Yes.
This isn't the time for a brainstorming meeting, right? You need established protocols for executing a massive product recall without hesitation or safely containing a sudden chemical emission. The alarms are ringing. People need to know their exact moves.
And that flows directly into training and equipping employees. The text makes it clear this isn't just about having a dusty safety manual on a shelf.
Right. In case of emergency, read page 40.
Exactly. That doesn't work. It means physically having the protective gear stored correctly on site and running the drills so the workforce knows how to deploy it under extreme stress.
The sources also talk about identifying alternative resources, too.
Yes. Well before you need them. If your primary manufacturing hub is submerged in floodwater, where's your backup workplace? If half your workforce is incapacitated, where are the temporary workers coming from?
So true. Now, the sources use two specific terms here for this survival phase that honestly sound identical to me at first glance, but the text treats them as distinctly different concepts.
Which ones?
Business continuity planning, or BCP, and contingency planning.
Ah, yes. The distinction there is vital for a resilient organization.
Okay, break it down for us.
Business continuity planning is the overarching framework. It's the broad structural philosophy of making sure the business can continue to operate and deliver value during major shocks.
Okay.
Contingency planning, on the other hand, involves the specific tactical alternate plans designed to facilitate success if certain isolated risk events actually occur.
Let me map that to something physical to make sure I'm getting it. BCP, business continuity planning, is the overarching strategic decision to always carry a spare tire, a heavy-duty jack, and an emergency flare kit in the trunk of your car.
Right, because your broad philosophy is that your vehicle must be resilient to road hazards.
Yes. The BCP is the architecture of your resilience.
Not on.
But contingency planning is having the exact step-by-step instructions memorized on how to safely change the front left tire on the side of a dark, rainy highway without getting hit by oncoming traffic.
Exactly. It's the hyper-specific, tactical execution for a defined event.
That makes perfect sense.
But the APCS materials emphasize one final, crucial piece to this whole recovery puzzle.
What's that?
After you use that spare tire, after the chemical spill is contained and the disaster has been managed, the job still isn't done.
Right, you can't just go back to normal.
No. Both the overarching BCP and the specific contingency execution must be followed by a rigorous phase of debriefing, analysis, and prevention.
You have to extract the data from the disaster.
Exactly. You take the hard lessons of how your contingency plan actually performed in the real world, and you feed that raw data directly back into the FMEA tool we discussed earlier.
Oh, wow. So you recalculate your risk priority numbers?
Yes. Was the severity of the flood worse than the matrix predicted? Did supply chain failure escape detection a week longer than you calculated? You update the math.
This feeds right back into the very top of the risk management process. Assess the strategy, identify the new reality, and begin the continuous loop again.
It never actually stops.
We have covered a massive amount of conceptual ground today. Let's do a fast-paced recap to lock this all in.
Sounds good.
We started by dismantling the illusion of a perfectly safe supply chain, looking at the myriad of threats, from a devastating external hurricane to the internal slow burn of bad spreadsheet math destroying inventory value.
The silent killers.
Yeah. We learned how to mathematically filter that panic using the FMEA to generate risk priority numbers, multiplying the occurrence, the severity, and that incredibly dangerous variable of escaping detection.
The hidden leaky pipe.
Exactly. We then took those scores and mapped them onto the risk matrix to visualize our battlefield, prioritizing where to spend money and where to strategically accept the risk. Finally, we built a resilient framework through business continuity planning and tactical contingency plans to ensure we can bounce back, debrief, and update the math when the worst inevitably happens.
This raises an important question, though, because risk management is not a textbook chapter you read once and put on a shelf.
Right.
It's a living, breathing audit of your own vulnerabilities. It requires a willingness to constantly confront uncomfortable realities about where your systems are weak.
Which actually brings me to a final thought I want to leave you with. When we discussed the 4 criteria for choosing a risk response earlier, one of them was evaluating the secondary risks created by the response itself.
Oh, that's a great point to zero in on.
Right. Does the solution create a brand new problem? So look around your own life, your own department, or your own business. Think about that leaky pipe hiding in the drywall. What is a safety net or a mitigation strategy you've confidently put in place that might secretly be creating a brand new, entirely invisible risk of its own?
That's a scary thought.
Because as we learned from the math today, the most dangerous failures aren't always the loud ones. They're the ones that escape detection until it's far too late. Thanks for joining us on this deep dive.